Hello my friends, I welcome you back for another tutorial of artificial intelligence. Don't forget to subscribe to my channel and don't forget to inform your friends to come and get this opportunity to learn about artificial intelligence. For those of you who are joining us for the first time, please go and read and watch the first videos about this course, because this is a series. I'm Luinga Hudson from Uganda. Feel free to contact me in case of any challenge. My email is there, and please feel free to also comment. Okay, this time we are going to look at the second part of problem solving. This lesson is going to cover searching types and their distinctions. So just like we said last time, we have two search strategies: uninformed search or the brain search, and then the informed search or the heuristic search. So we're gonna look at one by one. If we finish all of them, that will mark the end of the lesson. Now let's begin with uninformed search algorithms. We said that uninformed search algorithms have no additional information about the state or the search space other than how to traverse the trees, so they are called the blind search. So this is a class of general purpose search algorithms that operate in a brute force way. They are blind. They just have only information in the problem definition, no any other additional problem. So let's begin with the breadth first search algorithm. This is the BFS, in short, breadth first search. The breadth first search is the most common search strategy for traversing a tree or a graph. This algorithm searches breadth-wise in a tree or a graph, so that's why it's called the breadth first search. Breadth first search algorithm starts searching from the root node of the tree and expands all successor nodes at the current level before moving to the nodes of the next level. The breadth first search algorithm is an example of a general graph search algorithm. Breadth first search is implemented using the first in first out queue data structure. That's the FIFO. So let's have an example. In this tree, so this is an example of a graph that's a tree. So in this tree structure in this figure, we have shown the traversing. Traversing is when we are traveling through the nodes of a graph. So we have shown the traversing of the tree using the breadth first search algorithm from the root node S to the goal node K. So this is our root node S and our goal is K. Now the breadth first search algorithm will traverse in layers, so it will follow the path that is shown by these dotted arrows. It searches the breadth first. It will have to exhaust all the nodes on a certain level before going now down to the next level. So it will travel from S to A to B. So this is level 1. There's only one node it has exhausted. That's the starting node. So it goes to A. On level 1, we have two nodes, A and B. So breadth first, it will first traverse to B. Then it goes to C. Now on level where we have C, that's level 2, we have all these nodes. So it will have to traverse through all these nodes, so from C to D to G to H. After finishing all the nodes on that level, that is the breadth now, then it will continue to the next level 3 to node E, then F, I, and then finally K. So that's how we traverse a tree using the breadth first search algorithm. The advantages of the breadth first search is that, one, it will provide a solution if a solution exists, so it is complete. Then, if there are more than one solutions for a given problem, the breadth first search will provide the minimal solution that requires the least number of steps. Disadvantages is that it requires lots of memory, since each layer of the tree must be saved into memory to expand to the next level. So since on each layer the algorithm requires that it exhausts all the nodes on that layer or level, it takes a lot of memory. And another disadvantage is that it needs a lot of time if the solution is far away from the root node. Let's talk about the depth first search algorithm. The depth first search is a recursive algorithm for traversing a tree or a graph data structure. It's called the depth first search because it starts from the root node and follows each path to its greatest depth node before moving to the next path. Depth first search uses a stack data structure for its implementation, and the stack is the last in, last out. Last in, first out. That's the LIFO. The process of the depth first search algorithm is similar to that of the breadth first search algorithm. Let's look at an example. In this search tree, we have shown the flow of the depth first search algorithm, and it will follow the order as the root node, that's S on level 1, and our goal is G. So it will follow this order: root node, then it goes to the left node, that's A, and then to the right node. Okay. So it will start searching from the root node S and traverse to A, and then B. Remember, depth first, not breadth. So that's why it doesn't go to H, because if it goes to H, that is now breadth. But depth first until it finds the deepest node on the farthest level. So it will traverse from node S, that's the start node, to A, and then to B, then to D. Now D is now the deepest, so it cannot continue going down. After D, it will now go to E to exhaust all the deepest nodes. So E, and after E, it will do what we call the backtrack. So that's why it's called a recursive algorithm. It do backtracks. It goes now back to C, and it cannot go to this unless it first exhausts this. So after E, we are saying E has no other successor, and still the goal node is not found. So since there is no success of E and the goal node is not found, it will go to C, and from C it will find the goal G. So there's no need of this algorithm to go through H, I, J, and K. So we are saying that after backtracking, it will traverse to node C and then to G, and here it will terminate because it will have found the goal node. So what are the advantages of the depth first search strategy. It requires very less memory because it only needs to store a stack of the nodes on the path from root node to the current node. So as we have seen, there's no need of it traversing through all of these nodes as long as it has found the goal node. And it takes less time to reach the goal node as compared to the breadth-first search algorithm. Then the disadvantages: there is a possibility that many states keep reoccurring and there is no guarantee of finding the solution. The depth-first search algorithm goes from deep down searching, and sometimes it may go to the infinite loop. So it will go to a loop that doesn't end as it repeats searching, and it may not find the solution. Now let's look at number 3, the depth limited search. So the previous one was depth first search, but this one is depth limited. Now this search strategy is similar to the depth first search, but with a little difference. The difference is that in depth limited search, we limit the search by imposing a depth limit L to the depth of the search tree. It does not need to explore till infinity. So as a result, the depth first search is a special case of the depth limited search when the limit is infinite. Okay, so there's no big difference between this and the previous one, only that here we put a limit on the depth, what we call the depth limit L, to the depth of the search tree. Why? We are worried, we don't want our algorithm, as the goal-driven agent is searching using this algorithm, to go into an infinite loop that doesn't end. So we put a limit whether the answer is found or not, the solution is found or not. When the limit is reached, that's where the search will terminate from. Let's have an example. So here we are having a depth limited search on this binary tree. In this figure, the depth limit set is 1. So you are seeing this dotted line. That's the limit on level 1. So we are saying only level 0 and level 1 get expanded. So we have A to B, then to C. Now we cannot go to D because we shall be going to another level. So when we reach B, we go to C. But our goal, remember, when we look at the diagram, is I. So the depth first search sequence will start from root A till node B and then C. It is not giving a satisfactory result because we cannot reach the goal because of the depth limit. If there is no limit, we could reach the goal A, B. Remember, it uses it's like the depth first if there is no limit, so it would be A, B, D, M, then E, and then I. But now there is a limit, we cannot find the goal node I. So the advantages is that the depth limited search is memory efficient, so it doesn't take a lot of memory. And the disadvantage, as you could already be thinking about, is that it has that problem of incompleteness. So it may not be optimal if the problem has more than one solution. Now number 4 is the uniform cost search algorithm, UCS, the uniform cost search algorithm. The uniform cost search is a searching algorithm used for traversing a weighted tree or graph. Now, our intention here in artificial intelligence is not to exhaust, to go into detail of trees and graphs. That one is studied under design and analysis of algorithms or under data structures. So you can make more research, but in artificial intelligence, we are shown that you already have that background. Okay, we are saying that the uniform cost search comes into play when a different cost is available for each edge. The primary goal of the uniform cost search is to find a path to the goal node which has the lowest cumulative cost. The uniform cost search will expand nodes according to their path costs from the root node, and it can be used to solve any graph or tree where the optimal cost is in demand. So a uniform cost search algorithm is implemented using the priority queue. This algorithm gives the maximum priority to the lowest cumulative cost, and this algorithm is equivalent to the breadth first search algorithm if the path cost of all edges is the same. Let's have one example to understand it better. So here we are having a uniform cost search algorithm on a binary tree. In this figure, our goal state is if. So as we said, we can have two goals, and then the initial state is A. Now there are three paths available to reach the goal node. Okay? But we need to select the optimal path which may give the lowest total cost. That's the G of n in functions. So this one will now use the cost of each action that is taken to reach the goal, but it will take the optimal one, the lowest total cost. So therefore, when you traverse from A to B, the cost here is 1, then plus 3, that is from B to E. So we begin at 0 plus 1 plus 3, then here plus 4, giving us 8. So this is the lowest optimal, is the optimal path cost or the lowest total cost. And that's what the uniform cost search will utilize. Instead of going 0 plus 1, that is 1 plus 5. So once we go to this, that is 6 plus the 7. So that path will not work. It will be greater than this one. It's not the optimal path cost. So that's why we shall choose that. So that's how the uniform cost search works. An advantage for this kind of algorithm is that it's optimal because every state, the path with the least cost is chosen. Disadvantage, it doesn't care about the number of steps involved in searching and only concerned about the path cost, even if the steps are many. As long as the total path cost is the lowest, it will take that path. So due to the nature of this algorithm, it may also stuck in an infinite loop because it will only be considering the lowest cost path, and it can go back and back until it doesn't stop. So that's a danger for this kind of algorithm. Now number 5 is the iterative deepening depth first search algorithm, or simply iterative deepening search. The iterative deepening algorithm is the combination of the depth first search and the breadth first search algorithms. This search algorithm finds out the best depth limit and does it by gradually increasing the limit until a goal is found. So because it uses the depth first search algorithm and the depth breadth search algorithm, it will combine the benefits of the two, and therefore because of that, it will be fast, because the breadth first search is a fast algorithm, and again it will use less memory because the depth first search utilizes memory. Now this algorithm performs depth first search up to a certain depth limit, and it keeps increasing the depth limit after each iteration. So this iterative deepening depth first search algorithm is useful in uninformed search when the search space is large and the depth of the goal node is unknown. Let's look at this example. So this tree structure we are seeing is showing the iterative deepening depth first search. The iterative deepening depth first search algorithm performs various iterations until it doesn't find the goal node. So it will perform iterations until the goal node is not found. So that's when it will stop. The iteration performed by the algorithm is given as follows. In the first iteration, we have A. So there is no goal node found, so it will continue. In the second iteration, so it will go A, B, instead of going deep, because it uses breadth first and then depth first. We are saying that on the certain level, it will perform the depth first search for a certain limit, like on the limit of level 1, then it goes for the breadth. So we have A, B, instead of going to D, it will go to C. Then from there, in the third iteration, from C, in the third iteration, it will repeat. That's what I mean by iteration. Each cycle. So the first one is A, then A, B, C. Since there is no goal node, this time the iteration will be A, B. It will now increase its depth from level 1 to level 2. Remember, it uses the depth first search and the breadth first search. So the depth level will now increase from level 1 to level 2. So that will be A, B, D. So when it reaches D, it now goes breadth wise. So A, we have A, B, D, then E, F, G. Okay. Now, remember, on the third iteration, we are seeing the goal G, but we said it performs various iterations until it does not find the goal node. So it will continue still. Now it will increase its depth from level 1 to level 3. Since it's depth first, that means it will have to first reach H before it starts to go breadth wise. So you have A, B, D, H, then now breadth wise I, E, C, R, F, then K, and G. So you are seeing even if it reaches F, it has to go deep, then it goes back to G. So we are saying in the fourth iteration, the algorithm will find the goal node. So we shall stop there. Okay. Advantages of this search strategy. It combines the benefits of breadth first search and depth first search algorithms in terms of fast and the memory efficiency. So fast search is for breadth first search, and then depth search has that benefit of memory efficiency, so it will combine both benefits. One disadvantage or the drawback, the main one, is that it repeats all the work of the previous phases. As we have seen, for each iteration it will repeat what it has already done. Now we have what we call the bidirectional search algorithm. Bidirectional, bi means two, so two directions. Bidirectional search algorithm runs two simultaneous searches, one from the initial state, and that state is called the forward search, and the second one from the goal node, which is called the backward search, and it uses both of these two to find the goal node. The bidirectional search replaces one single search graph. So instead of having one single search graph, it replaces it with two small subgraphs, in which one starts the search from an initial vertex and the other starts from the goal vertex. The search will stop when these two graphs intersect or meet. The bidirectional search can use any search technique such as the breadth first search, the depth first search, depth limited search, and so on and so forth. So this is an example. In this search tree, we have the bidirectional search algorithm being applied. So this algorithm divides one graph or the tree into two subgraphs. So this is one graph, and this dotted line tries to show the division. Now it will start traversing from node 1, the root node, in the forward direction. So that's the forward direction. And it will also start traversing from the goal node, that is node 16, in the backward direction. So that's the backward direction. Now this algorithm will stop or will terminate at node 9. That's the node where these two traversals shall meet. So that's when it will stop. What are the advantages? This search is very fast and it requires less memory because it employs two kinds of searches. That means it's fast. The disadvantages: the implementation of this kind of search is difficult, and in this search one should know the goal state in advance, because the goal state is also used in the backward direction. We begin from the goal node, so you have to know it in advance before you employ this kind of search. So far we have talked about the uninformed search algorithms, and these looked through search space for all possible solutions of the problem without having any additional knowledge about the search space. But informed search algorithms contain an array of knowledge, such as how far we are from the goal, the path cost, how to reach the goal node, and so on. So unlike the previous search algorithms, the uninformed, these informed search algorithms will contain an array of knowledge, additional knowledge. How far are we from the goal? So as the agent is traversing, as it employs this algorithm to search, it will have that knowledge. How far is left to reach the goal? What is the path cost of the path that I'm going to reach at any state? And how am I going to reach the goal node? So this kind of knowledge helps agents to explore less to the search space and find more efficiently the goal node. So the informed search algorithm is more useful for large search space. Informed search algorithm uses the idea of heuristics. So it is also called the heuristic search. So they use what we call the heuristic functions. Now, a heuristic function is a function which is used in informed search, and it finds the most promising path. So it takes the current state of the agent as its input and produces the estimation of how close the agent is from the goal. The heuristic method, however, might not always give the best solution. Yeah, it might not give the best solution, but it's guaranteed to find a good solution in reasonable time. So given the reasonable time, it can find a good solution, much as it may also not be the optimal one. So the heuristic function will estimate how close a state is to the goal. So that's the work of the heuristic function. It will estimate how close a state is to the goal, and this is represented by h of n in function notation, heuristic h for heuristic h of n, and it calculates the cost of an optimal path between the pair of states. So the value of the heuristic function is always positive. Now we have what we call the pure heuristic search. Pure heuristic search is the simplest form of the heuristic search algorithms. It expands nodes based on their heuristic value, based on the function hn. It maintains two lists. We have what we call the open list and the closed list. Now in the closed list, it places those nodes which have already expanded, and in the open list, it places those nodes which have yet not been expanded. Now on each iteration, each node with the lowest heuristic value is expanded and generates all its successors, and that node is placed to the closed list. This algorithm will continue until a goal state is found. So we have an example of the pure heuristic search algorithms. So we have the best first search or the greedy search. A best first search is a general approach of informed search. Here, a node is selected for expansion based on an evaluation function, fn, that's the evaluation function, where that function fn interprets the cost estimate value. The evaluation function will expand that node first, which has the lowest cost. So at every state, we have to look at the node which has the lowest cost. That's what will be considered. A component of f of n is the h of n, that's the heuristic function. So it's a component of the fn, which fn is the evaluation function. And that hn carries the additional information required for the search algorithm. That is, h of n is equivalent to the estimated cost of the cheapest path from the current node n to the goal node. So that's the additional function. What's the estimated cost and what's the cheapest path at the current node to the goal node? You have to note also that if the current node n is a goal node, the value of the heuristic function hn is 0, because if the current node now is the goal, so the cost path will be 0. So the heuristic function, which function carries the additional information required for the search algorithm, will hold the value of 0 as its estimated cost. the best first search, remember this is not breadth first but best first. So the best first search algorithm is also known as a greedy search because it will always try to explore the node which is nearest to the goal node and selects that path which gives a quicker solution. So before even this path goes ahead to find, before this algorithm looks for that path with a quick solution, it will always try to look for the nearest node that is near to the goal node. So that's why it's greedy. It will try to explore the node which is nearest to the goal node, and it will select that path after, which gives a quick solution. Therefore, it will evaluate the nodes with the help of the heuristic function. So it will evaluate a node whose heuristic function holds a value that is the cheapest. So where the f of n, that's the evaluation function, is equivalent to the h of n, the heuristic function. So these are the steps involved in the best first search algorithm. Step 1, place the starting node into the open list. Remember we said you have two lists. So place the starting node into the open list. Step 2, if the open list is empty, stop and return failure. Step 3, remove the node n from the open list which has the lowest value of the heuristic function hn and place it in the closed list. Step 4, expand the node n and generate the successors of node n. And 5, check each successor of node n and find whether n node is a goal node or not. If n successor node is a goal node, then return success and terminate the search, else proceed to step 6. And step 6, we are saying for each successor node, algorithm checks for evaluation function fn and then check if the node has been in either open or closed list. If the node has not been in both lists, then add it to the open list. And step 7, return to step 2. That is, if the open list is empty, stop and return failure. Okay, we are going to use an example to try to see how the breadth first search algorithm works and how this algorithm works. Now in this example, we have this figure and our root node is A and its next level successor, the next level successor nodes of A. Of course, you are seeing the successors of A. We have B and C. These nodes that are directly connected to A, below A, are called the successors. So if I could ask you the successors of C, the answers would be F and G. So we are saying it will look for the path that is nearer to our goal and it will take the one that is shortest. So we have B and C. Which one is shortest? Of course 2. 2 is shorter than 4. That means h of B, the heuristic function of node B. Remember we normally use hn. That means heuristic function of a certain node. Now our node instead of n we have B because we are looking at node B. So h of B is 2 and h of C, the heuristic function of C, has a path cost value of 4. So our task is to explore that node which has the lowest value, h of n. And according to us, it is 2. So it will take a B instead of a C. So That's why we will select node B and expand it further to node D and G. Again, we have to search out that node which has the lowest heuristic function value. So we have h of D and h of E. H of D will be 8, whereas h of E is 1, meaning we shall take this root. So we shall have A, B, E, and so on and so forth. So that's how the best first search algorithm works. Advantages: it can switch between breadth first search and the depth first search by gaining the advantages of both algorithms. So it can go breadth first or depth first depending on the path cost on given nodes. So meaning it can have both the advantages of the BFS and the DFS. This algorithm is more efficient than the breadth first search and the depth first search. So when you compare this algorithm with these other two, it is more efficient. Disadvantages: it can behave as an unguided depth first search in the worst case scenario. So a depth first search without a limit, this one can also behave that way. It can also get stuck in a loop, just as the depth first search, and this algorithm is not optimal. Okay. Another example or another type of the heuristic search algorithms is the A** search algorithm. Now, A** search is the most commonly known form of the best first search algorithm. It uses heuristic function. So this is also another form of the the best first search, but it also uses a heuristic function and the cost to reach the node N from the start state Gn. So this one uses 2. It has Gn and the h of n. The h of n is the heuristic function, and then the cost to reach the node is the g of n. It has combined features of uniform cost search and the greedy best first search algorithm, by which it solves the problem efficiently. Now, this A** search algorithm finds the shortest path through the search space using the heuristic function. This search algorithm expands less search tree and provides optimal result faster. The A** algorithm is similar to the uniform cost search, except that it uses g of n plus h of n instead of only g of n. Remember, g of n is the cost to reach the node, and the h of n is the heuristic function. So, for that matter, we can combine both costs as the sum to obtain a fitness number. So it will use a fitness number. This fitness number is the combination of the cost and the cost, the cost to reach the node and the heuristic function value. When you combine the two, the sum of g of n and h of n gives us the fitness number. So it will base on this fitness number to traverse a tree or a graph. So this is what we mean. We have f of n, the function using the A** search will have a combination of g of n, that's the cost to reach the node n from the start state plus the cost to reach from node n to the goal node. Okay. And the combination of these two will give us the estimated cost of the cheapest solution. G of n is cost to reach node n from start state. So from start state up to a certain node, what's the cost? But this h of n, the heuristic function value, is the cost to reach from the node to the now the goal node, not the start but the goal node. So a combination of the two gives us what we call the fitness number, and it's the fitness number that will be used to decide which node to take. So that's how the A** search works. We are saying that at each point in the search space, only those nodes are expanded which have the lowest value of f of n, and the algorithm terminates when the goal node is found. So this is the algorithm. You can read through it. I'm just going to explain how we use that algorithm on the next slide. So let's have this example. In this example, S is the root node, and G, this G here, is the goal node. So when we start from S, our root node, and we move towards either A, so from S, we have to move towards either A or B. In order to reach the goal node, which is G, we have to calculate the f of n, the function value on each node, f of n. Okay? Now, we are going to use this equation that we talked about. The f of n is equal to g of n plus h of n. So when we are at node S, that means we have f, our node n now is S, so we have f of s is equivalent to distance from S to S. Remember, that is the g of n, the distance from the start node to the current node. So since we are moving from S to S, of course, that is 0, plus h of s, that's the distance from node S to the, it is estimated to the goal. So it is given here, it is 10. So that means we have 0 plus 10, giving us 10. So f of s is 10. Now if you want to calculate f of n for node A, that is f of a, distance first of all from S to A is 2, and then distance from A to the goal node G is given here, the heuristic value, as 12. So that means we have 2 plus 12, which is 14. But now f of b, from S to B, we have 3, and then h of b, from the key here, h of n is the one in red and g of n is in black. So h of b is 14. So you're seeing 14 here. That means we have 3 plus 14, which is 17. So when you compare f of a that we got as 14 and the f of b, which is 17, A has the lowest f of n value. Hence, node A will be explored at this level. Then on the next level, you also compare nodes C and D, and again you calculate f of C and f of D. After that, you will have the final sequence as S, A, D, and G. So the difference between this A** search and its predecessor, the best first search, here we not only look at the heuristic value, the value of the heuristic function, but rather we also look at the value, the cost value from the start node to the current node. Then a combination of the two will give us the fitness number, which fitness number we shall compare, and we shall choose the one with the lowest value. So the final path of traversing this tree will be S, A, D, and then G. Okay. Now, the advantages of this algorithm, we have one, it is the best algorithm than other such algorithms. It is optimal and complete, and it can solve very complex problems. Disadvantages, it doesn't always produce the shortest path, as it's mostly based on heuristics and approximations. And the Heuristic Search algorithm has some complexity issues. So when you talk about complexity, remember we said we can define complexity in two aspects: the time complexity and the time complexity and memory, or the space complexity. But the main disadvantage or the main drawback of the Heuristic Search algorithm is that it requires more memory, because it keeps all the generated nodes in the memory, so it's not practical for some large-scale problems. Friends, I thank you again for watching my videos. Please feel free to comment. Don't forget to subscribe to my channel, and please invite more of your friends to come and also enjoy these tutorials about artificial intelligence. Let me leave you with this quotation from Eliezer Yudkowsky. He says, "By far, the greatest danger of artificial intelligence is that people conclude too early that they understand it." So members, don't fall into this trap. Please come back and enjoy more of the tutorials. God bless you.